Hey everyone, and welcome to the second video of the Year 11 Specialist Combinatorics unit. This video is going to deal with the first sort of counting principle that we formally introduced, the other one being the pigeonhole principle, and I've got a separate video that's going to be coming up next, which is dedicated to that one. So this is one of the counting principles. In terms of the unit outline, I'm going to introduce what the inclusion-exclusion principle deals with. It kind of goes into set theory, and you'll be dealing with using the inclusion-exclusion principle as a counting technique for something involving 2 sets and something involving 3 sets. And you'll see how the inclusion-exclusion principle ties into set theory and that sort of stuff when I give some examples and go through worked solutions. So let's get straight into the video. Okay, so now that I'm introducing the inclusion-exclusion principle, what I'm going to do is I'm going to look at, first of all, the set theory for the union of 2 sets, and then introduce a question related to that. And then I'm going to look at the set theory associated with the union of 3 sets and a question associated with that. So if we start now first with the union of 2 sets, essentially what the pigeonhole principle involves is we have our two events here, and we can represent those with A and B. And what the pigeonhole principle says is that the number of elements in A or B is going to be equal to the number of elements in A plus the number of elements in B minus the number of elements in A intersect B. And I can also equally write that as the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. And the reason why that's the case is because I can just divide all of these, both the left-hand side and the right-hand side, by the number in the union. Okay? And that's something mathematically that we can do, and that gives us this probability. So that's how we get from equation 1 to equation 2. All right, so that's essentially what the pigeonhole, that's what the inclusion-exclusion principle tells us, okay? And the reason why it works is if we look at A as this point here, and then we look at B in this form here, what we can see is if we add A and B, what we're going to do is we're going to count the intersect of A and B twice. And so we need to subtract it once. And in doing so, we count each position in the union of A and B once. Okay? And that's how we get these formulas. All right? Let's say we are thinking about numbers between 1 to 50 inclusive. And let's say our event A is where it is divisible by 3, and our event B is where it's divisible by 4. What we want to find is how many numbers between 1 to 50 inclusive are divisible by 3 or 4. So in order to do that, we first need to consider the cases where they're divisible by 3. Then we need to consider the cases where they're divisible by 4. And then we need to consider the cases where they're divisible by 3 and 4. The way that we can represent divisible by 3 and 4 is that they're divisible by the lowest common multiple of 3 and 4. The lowest common multiple of 3 and 4 is 12. So if we want to count the numbers between 1 to 50 inclusive, what that's going to be equal to is 50. We're going to have 50 numbers, right? We'll have 50 numbers. So if we have 50 numbers and we want to calculate the number that are divisible by 3, we can simply divide 50 divided by 3 and find the floor of that. What this floor means is that whatever value we get, we're going to round down. The reason why we have to round down is if this gives us a value, let's say this gives us 18.5, and we rounded up, that would mean that we're considering a number outside of the range. So let's say in this case, 51, for example, is divisible by 3. If we round up, we're including 51, but we only have 1 to 50 inclusive. So this would be incorrect. And so what we have to do is we need to find the floor. The maximum number from 1 to 50 that's divisible by 3 to be precise is 48. So if we plug this into our calculator, we divide 50 by 3. What we will get is 16.6 recurring. But because we're finding the floor of this, we need to round down to 16. So this is the number that are divisible by 3. Now if we want to find the number that are divisible by 4, what we do is we divide 50 by 4 and find the floor of that as well. 50 divided by 4 is equal to 12.5, but because we're finding the floor, we need to round down to 12. Finally, divisible by 3 and 4 is equivalent to dividing 50 by 12. Okay? 50 divided by 12 is equal to 4.16 recurring, but because we're finding the floor, you round down to 4. So the number that are divisible by 3 and 4 is going to be equal to 16 plus 12 minus 4, according to the pigeonhole principle. That is equal to 24. And so this is an example of the use of the pigeonhole principle for 2 sets. Now, when it comes to 3 sets, it gets a little bit more complicated. When we're dealing with 3 sets, we have an A, we have a B, and we have a C. Okay? A, B, and C. The pigeonhole principle says that the union of A, B, and C is going to be equal to A plus B plus C minus A and B minus A and C minus B and C plus N, A and B and C. And equally, we can write that for probabilities, okay? Because of the math that's associated with that. Now, the reason why that is the case is because when we count this, let's say we have A here, and we have B in pink here, and then we finally have C in purple. What you can see here is that this bit here is counted twice. So we need to subtract that once. This is also counted twice. This is also counted twice. So by subtracting each of those, we only count each of these once. Okay? However, notice that when we subtract them 3 times, okay, we're also subtracting this central bit 3 times. Okay? So if we count the central bit in terms of adding A, B, and C, we count that central bit 3 times. Once by counting it with respect to A, the second time by counting it with respect to B, and the third time by counting it with respect to C. When we subtract these intersections each time, we subtract each of those times that we counted it. And as a result, what we end up with is we've counted everything except the center. And as a result, we're going to need to add that center back, and hence we have that thing right at the end. Let's say we have a question, and we're trying to find numbers from 1 to 100, and we want to find one that's divisible by 2, 4, or 7. Okay? In this case, we're going to need to consider a bunch of different cases. So, first of all, we need to consider divisible by 2, then divisible by 4, then divisible by 7, then 2 and 4, then 2 and 7, and then 4 and 7. And then we also need to consider the case where they're all divisible for this scenario here. Okay? So if we want to do that, divisible by 2 and 4, that's going to have to be 4, right? Because everything that's divisible by 2 is divisible by 4. So that's the lowest common multiple of 2 and 4. If we want to find 2 and 7, the lowest common multiple here is 14. The lowest common multiple of 4 and 7 is 28. And the lowest common multiple of 2, 4, and 7 is going to be 14. Okay? Sorry, 28. That's wrong. 28. Okay? That's the lowest common multiple of 2, 4, and 7. So if we want to find the lowest common multiple, if we want to find the number of numbers that are divisible by 2 from 1 to 100 inclusive, that's going to be 100 numbers. And so the number of numbers that are divisible by 2 is going to be given by the floor of 100 divided by 2, which in this case is 50. 100 divided by 4 will give us 25 numbers. 100 divided by 7, the floor of that will be a number that is 14.285, etc., etc. Because it's the floor, we need to round down to 14. Now we deal with the cases where there are multiple. The lowest common multiple of 2 and 4, to find the numbers that are divisible by both 2 and 4, that's just going to be 100 divided by 4, which in this case is 25. 2 and 7, it's going to be 14. So 100 divided by 14, in this case, is 7.14, but because it's the floor, we get round down to 7. Then 100 divided by 28 for the numbers that are divisible by both 4 and 7. 100 divided by 28 is equal to 3.57, etc., etc., because we're finding the floor 3. Now the numbers that are divisible by all 3 of them is given by 100 divided by 28, the floor of that, which is 3. And so the total number of numbers from 1 to 100 inclusive that are divisible by 2, 4, or 7 is going to be equal to 50 plus 25 plus 14 minus 25 minus 7 minus 3 plus 3. And what that is going to be equal to, if we put that into our calculator, that is going to be equal to 57. So this sort of problem is one of the most common inclusion-exclusion principles that you deal with, more specifically that divisibility problem. 3 sets is generally a little bit more difficult to understand conceptually. Just make sure you re-watch this video a couple of times and maybe try to work it out yourself, so you can see it sort of work spatially in terms of how many times you count different sections of the Venn diagram. But yeah, overall, that's everything from the inclusion-exclusion principle. If you have any more questions, make sure you post those in the comment section. Otherwise, I will see you in the next one. Thanks, guys.